We now turn our attention to unit length vector. The vector is, as we have just done, are the vectors, for example, in our R2 or R3 space. The word unit length here means that this vector, the norm of this vector, has unit length, and unit length is 1. To get a unit length vector, for example, if v is a vector and does not have unit length, all we need to do to get a unit length vector along the direction of v is to divide v by its norm. Let's call this unit length vector of v as u. U is equals to v divided by the norm of v. Why is this so? Remember, in our last expression in the theorem, the norm of u is equals to k times v, where k is the scalar and v is the vector, and the norm of u is equals to bringing out the k, the absolute value of the k, multiplied by the norm of v. If k is equals to 1 over norm of v, therefore we'll have this expression here, norm of v divided by norm of v, therefore indicating that our norm of u is equals to 1. This process of multiplying a non-zero vector by the reciprocal of its length, reciprocal means 1 over the length is the norm, this is called normalizing the vector v to get a unit length vector pointing at the direction of v. This is an R3 example. We will find the norm. We will divide the vector v by the norm. Working through the examples, what we will see is that the new value is this. The normalized u, the unit length vector of v is equals to 1 over 3, the original components of v. You should always also check that the norm of u is 1. Why are we interested in unit length vectors? Well, in this example, the unit length vector is a hat. Any vectors a in this example can be represented as a scalar value multiplied by the a hat, the unit length vector. 2.5 basically means that the length of a is 2.5 times longer than the unit length vector a hat, and it is pointing to the same direction as a. In the last slide, basically we have further examples in R4 to find the unit length, and I'll leave it to you to do these examples by yourself. What is interesting is that sometimes we express length, the norm of the vector, as well as the square of the norm of the vector. And in the next slide, 6.1.3, we'll realize that the square of the norm of the vector can be found by the dot product of the vector. In this example, we are interested to find the distance between two vectors. Or here the word distance basically means the Euclidean distance, and we can use the norm. The norm of what? The norm of a vector between u and v. Let us have this concrete example. U is a R2 vector at position 7, 1. This is 7 and the vertical axis is 1. So u is equals to 7, 1 as a column vector representation, or as a tuple representation 7, 1. V is a vector with coordinates 3, 2. This is 3, this is 2, 3, 2. We can, therefore, by visual inspection, find this vector from V to Q, which is 1 position, 2 position, 3 position, 4 position to the right hand side, 4 on the horizontal axis, and 1 position down from the vertical axis. Let us call this vector Q. Therefore, if we start from the origin and we want to go to position or point V, it is V. And from V, we want to go to position Q, is plus Q. Therefore, the final position is equals to U, implying that Q can also be calculated as U minus V. And if we want to find the length of Q, all we are doing is taking the norm of this vector, which is taking the norm of U minus V. Concretely, this is shown in this equation over here. Therefore, to generalize, examples show us how to find the norm of or the distance between U and V. In this general example, U is given with coordinates U1, U2, U3, and V is given coordinates V1, V2, V3. The distance, or we should say the Euclidean distance between U and V, is using U minus V with the coordinates and taking the norm, which is simply doing it this way as well on the right hand side. Or more concretely, basically subtracting individual coordinates, squaring it, and sum and taking the square root. This concludes our discussion of 6.1.2.